Hello, this is Mr. Brooks and welcome to Lesson 7.4, Similarity in Right Triangles. In this lesson, we're going to find and use relationships in similar right triangles, and so we can find the distance indirectly once again. The first theorem in Lesson 7.4 states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Okay, let's see if we can understand what that means. Okay, if we look at triangle ABC, which we can see is a right triangle because angle ACB is a right angle, the altitude to the hypotenuse is segment CD. For triangle ABC, the altitude to the hypotenuse is segment CD. Segment CD breaks the big white triangle into two smaller triangles. This triangle and this yellow triangle. So again, what this theorem is stating is that the white triangle, the blue triangle, and the yellow triangle are all similar. That means all their angles are congruent and all their sides are proportional. So first let's look at the smaller blue triangle, triangle ACD. Hopefully you'll agree angle A corresponds to angle A. Alright? Angle D of the blue triangle is the same as angle C of the white triangle. So angle C of the blue triangle corresponds to angle B of the white triangle. Now let's look at the yellow triangle. Angle D of the yellow triangle corresponds to angle C of the white triangle. Angle B of the yellow one corresponds to angle B of the white one, and angle C of the yellow one is going to correspond to angle A of the white one. Before we go any further, we have to discuss what the geometric mean is for two numbers. Your book says geometric mean for any two positive numbers, A and B, is the positive number x such that A over x equals x over b. Let me write that down. A over x has to equal x over b. All right, now let me give you an example so we can understand this better. So example 1 asks us to find the geometric mean of 4 and 18. So we're going to set up a proportion. We're going to write 4 over x, which has to equal x over 18. All right, now, of course, as always, we're going to do cross products. So x squared is going to equal 4 times 18. So x squared has got to equal 72. Then we take the square root of both sides. So the square root of x squared is x. So the geometric mean of 4 and 18 is going to equal the square root of 72. And hopefully you'll agree that would be the same as 36 times 2. So we get the square root of 36 times the square root of 2, which is 6 times the square root of 2. Now, quick trick number 1 asks you to find the geometric mean of 15 and 20. Please pause the video while you try to figure this out. Alright, again, the first thing we're going to do is set up a proportion. 15 over x equals x over 20. Then again, you're going to do cross products. So x squared, x times x, is going to equal 15 times 20. So x squared is going to equal 300. Then you're going to take the square root of both sides. Square root of x squared is x equals the square root of 300. And as we said before, we're going to find a perfect square that goes in there. 100 times 3. So it's a square root of 100 times the square root of 3, which is 10 times the square root of 3. The geometric mean for 15 and 20 is 10 times the square root of 3. Our first corollary to our last theorem. Now remember, a corollary is just an extension to a theorem. So this corollary to Theorem 7.3 states The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. All right, let's see if we can figure out what this means. Okay, once again, if we look at triangle ABC, the white triangle, segment CD is the altitude to hypotenuse. What they're saying is CD is the geometric mean for these two parts of the hypotenuse, AD and BD. So let me write it down. AD over CD. Again, CD is the geometric mean for AD and BD. Now let's look at number 19 from the homework to see if we can better understand this. Again, the altitude to hypotenuse, in this case x, is going to be, x is the geometric mean of the two parts of the hypotenuse, 16 and 9. So, to solve this, we're going to do, once again, cross products. X squared is going to equal 9 times 16. So, x squared is going to equal 144. Take the square root of both sides, and so x equals 12. Our second corollary to theorem 7.3, and possibly the most single complicated and confusing sentence in our entire geometry book, states, the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. That is a pretty heavy statement. Let's see if we can better understand it. Once again, let's look at triangle ABC with the altitude of the hypotenuse being CD, again, to see if we can better understand this. What they're saying is that each leg of the white triangle, in this case AC, is a leg of the right triangle. So AC is the geometric mean for AD, that part of the hypotenuse, and the entire hypotenuse, AB. And they are also saying that CB is going to be the geometric mean for BD, that part of the hypotenuse, and the entire hypotenuse. All right, let's look at it one more time. This time we're going to let these lowercase letters be the segments themselves. So A is the geometric mean for B and B plus C. D is the geometric mean for C and B plus C. Again, the legs of the white triangle, which in this case are A and D, are the geometric mean for the adjacent part of the hypotenuse and the entire hypotenuse. Okay, let's look at a specific example and see if we can figure out what that second corollary is talking about better, and the first corollary for that matter. All right, to get y on example 2, we're going to use the first corollary. It says the altitude of the hypotenuse, y in this case, is the geometric mean for the two parts of the hypotenuse, which in this case would be 4 and 5. So, doing cross products, y squared is going to equal 20. Take square root of both sides, so y equals the square root of 20. Then simplifying radicals, y equals the square root of 4 times the square root of 5, so y equals 2 times the square root of 5 is your full credit answer for y. Now, let's see if we can get x. X is the geometric mean for the adjacent part of the hypotenuse, which is 4, and the entire hypotenuse, which is 4 plus 5. So x over 4 is going to equal 9 over x. Again, doing cross products, we get x squared equaling 4 times 9. So x squared equals 36. Take the square root of both sides, and you get x to equal 6. So our two answers, for example 5, x equals 6, and y equals 2 times the square root of 5. All right, now let's see if we can do quick check number 2. Please pause the video while you try to figure out x and y. All right, to get y, we're going to use the first corollary that says the altitude of the hypotenuse, which is y, is the geometric mean for the two parts of the hypotenuse, 4 and 12. So y squared equals 4 times 12. Y squared is going to equal 48. Then you take square root of both sides, so y equals the square root of 48. Again, a perfect square that goes into 48 is 16 times 3. So y equals the square root of 16 times the square root of 3. So finally we get y to equal 4 times the square root of 3. Now let's see if we can get x. X is the geometric mean for the adjacent part of the hypotenuse, which is 4, and the entire hypotenuse, which is going to be 4 plus 12. So x is the geometric mean of 4 and... So to solve this, once again, we're going to do cross products. So x squared is going to equal 16 times 4. X squared equals 64. Take square root of both sides, and you get x to be exactly 8. Example 3 and quick check number 3 we will go over in class. So this concludes lesson 7-4.